The next kind of layers we will study are these recurrent layers. And the recurrent layers are meant to handle with sequences. So here, for instance, let's say that we have this sentence. It is a period of civil war and whatever. So our network, the goal or the task of our network is to remember this text. So it will take groups of 3 previous letters, and it has to predict the next one. So given I, T, and space, it has to predict I. Given T, space, and I, it has to predict S. Each one of the letters has its own one-hot encoding. So we already know how these things work. So if we compare the standard neural networks, these dense neural networks that we have studied so far, so we would have an output for each one of the classes. So whether it is letter I or it is letter T or space or whatever, each one of these outputs would be one of those letters. So the one-hot encoding. So each one of those letters. But these networks cannot reuse the information from the previous state. It doesn't have the concept of a state or the previous prediction. So these are given an input, they produce an output. They are called feed-forward neural networks. The recurrent neural network now, the input or the output can become its own input. Here there is a reversed arrow. So this is a mistake. So these feedback loops, they give the network memory. So now it can handle sequences. So it is somehow like also in this representation. So you have a system, then you have an input to the system, and this system is producing an output that is called the hidden state, and that state somehow the system is affecting itself. And in practice, what you do is you unwrap this system for a finite number of cycles. So x0 is affecting the first system, but the state of this system is affecting the state of the next one that is receiving x1. So you repeat that for the length that you want, and then you don't have an infinite recurrence as in here, but a finite recurrence. So what kind of network or what kind of layers we can have that there? So these layers was one of the first ones to design for this recurrence. So it was the recurrent neural network. So the recurrent neural network had an internal state that was called the hidden state. So it has the output as usual. So this is just a dense connection. So you have, but the dense connection is not done through the input. It is done through the state. So the input affects the state, and the state affects the output. So and the way to affect is just the standard one. So this is just the standard dense neural network or dense layer, but now it has two components, one coming from the input, now coming from the hidden state plus the bias. And the problem with this network is that it has a vanishing gradient. So as you get further and further in this progression, the output here has very little chances of propagating back the error to the first layers. So this vanishing gradient was a problem for learning. And also there is a comment here. So the very first network, or the very first element in the chain, you have to initialize to something. So typically it is 0 or a constant or randomly, or you learn. It is a parameter that you have to learn. So this network had, or this layer had, the problem of the vanishing gradient. So the next refinement of that idea was these gated recurrent units. So gated recurrent units, they also have an internal state, this hidden state, but now it is handled in a different way. So you will create a hidden state. This hidden state is partly computed, so this set is a kind of mask. So the mask is a function of the input and the state, and the previous state. So this is just a dense neural network. And then you have this is a mask between the previous state and the new candidate. So the new candidate is computed in this way. So the new candidate, yeah, by the way, this is a representation of, you have a long matrix, there is an upper block, a lower block. This is the concatenation of the two vectors. So this is a convenient way of writing kind of this sum. Okay, so you have in this mask is set to, yeah, so this is what the new state, how it will be updated. So it is a mixture between the new one, or sorry, the old one and the new one. And the new one somehow is also using just a standard dense neuron, but and it is somehow a hyperbolic tangent, so it is between 0 and 1. So here this one can be interpreted as a reset gate. So this R is a reset gate. So you are learning something to reset. So something to reset. So in the input, so given this input and this, so given this input and this state, you will reset something. And then this reset something is somehow forgetting your previous state at the specific locations. So now you have two parts. One that is somehow learning new information, the other one that is forgetting new information, old information. So this part of forgetting was shown to help a lot during the convergence and the optimization of that networks. And there is even an even further refinement. So now instead of having one state, you will have two states. One that is called hidden state, the other one that is the cell state. So now you have this kind of gates, so how much to forget from the previous and how much you want to take from the input, and then how the previous and the current input will affect the output, and then you have the update equations for each one of the states. So you have a candidate cell state, and then with the candidate cell state you update your cell state as we did before, but now these two are independent. So before they were coupled, so this is set of t, this is 1 minus set of t. So now you are free to learn two different functions, and then you update your hidden state with your output and your cell state. So different refinements of the same idea. So something to forget depending on what is the input, something to remember depending on what is the input, some way to generate the output, and some way to update the internal state. This one, I think it is one of the current state of the art in these sequential neural networks. It is this long short-term memory cells. And all these networks somehow are recurrent, but they have a directionality. So the input, the first token affects the interpretation of the second, the first and second affect the interpretation of the third one, and so on. What if, for instance, we have a sentence like Apple announced the new iPhone in September, and we want to understand what are the different names of organizations, people, locations. So Apple could be both, could be, so it is the first token that we find. So it could be both, it could be a company, but it could also be a fruit. So how do we distinguish between those? So in this unidirectional sequence analysis, we cannot know. After just seeing the word apple, we cannot know what it is. So you have the information from the rest, from the last part of the sentence. So this iPhone September makes that this apple cannot be the fruit, it has to be the company. So what that means is that you have to process the data bidirectionally. So you have from the first element to the last one, but then this one is you have the standard from left to right reading, so this network, and you have from right to left reading. So you have now two chains of states and output. So one coming from the left to right, another one coming from the right to left, and then the last output. So the output that you use is a mixture of the states and the outputs of the left to right and right to left. So these are called bidirectional recurrent networks. So if you want more information about recurrent layers and recurrent networks, I recommend you these links, and this would be it.